Hello, focused learners, and welcome to this explainer. I am absolutely thrilled you're joining me today because we're looking at something truly foundational. We are talking about carbon. Now, I don't want you to just picture some dusty chemical element on a periodic chart. No, I want you to think of carbon as the ultimate Lego brick of the universe. It is quite literally the fundamental building block of almost everything around you, including you. Okay, let's dive into this. Here's our roadmap for today. Number 1, we'll meet the ultimate builder. Number 2, the shape-shifting allotropes. In part 3, we'll explore chains, rings, and hydrocarbons. Fourth, carbon in everyday life. And finally, a carbon chemistry pop quiz.
Section 1. Meet the ultimate builder. Understanding the carbon atom.
So, there are a lot of non-metals out there, right? What makes carbon, chemical symbol C, so incredibly special compared to all the rest? Why does it literally get its own branch of chemistry? Well, to answer that, we have to start with the number 6. That's carbon's atomic number. It tells us its fundamental identity and exactly where it lives on the periodic table. Basically, it means every single carbon atom has exactly 6 protons in its nucleus. But the real magic of carbon isn't just about the number 6. It's actually about what happens on the very outside of the atom.
And that brings us to the number 4. This is the secret ingredient to carbon's massive success. Carbon has 4 valence electrons. Those are the electrons hanging out in its outermost shell. In chemistry, we call this property tetravalency, with tetra meaning 4. And this tetravalency is exactly what allows carbon to be the absolute greatest builder in the microscopic world. Let me explain how that actually works. Because it has those 4 outer electrons, carbon just loves to form what we call covalent bonds. Now, a covalent bond is simply a super strong chemical bond formed when atoms share their electrons with one another. Think of carbon exactly like a standard square Lego block that has 4 connecting pegs right on top. Or, if you prefer, imagine a really friendly person with 4 arms who is constantly looking for 4 handshakes. Carbon uses those 4 connecting points to grab onto other elements like hydrogen, oxygen, nitrogen, and most importantly, it absolutely loves to grab onto other carbon atoms. Section 2. The shape-shifting allotropes. Same building blocks, different forms.
First, let's clearly define that term. An allotrope refers to the different physical forms in which a single chemical element can exist. It is totally fascinating how nature can take the exact same ingredient, pure carbon, and by just snapping those Lego bricks together a little differently, produce materials that are practically opposites.
The most famous example of this contrast is diamond versus graphite. On one hand, you have diamond. It is the hardest known natural substance. Why? Because every single carbon atom is rigidly bonded to 4 other carbon atoms in an incredibly dense 3D crystal lattice. It is locked in tight. On the other hand, you have graphite. It's incredibly soft, it's slippery. Actually, you use it every time you write with a pencil. In graphite, the carbon atoms form flat sheets that just slide right over each other. Same exact atoms, entirely different structures, and entirely different properties.
And our understanding of these allotropes has really evolved over time. Since ancient times, humans have known all about diamond and graphite. But fast forward to 1985, and scientists discovered fullerenes, which are often called buckyballs. These look like microscopic, hollow soccer balls made entirely of 60 carbon atoms. Then, in 2004, we isolated graphene. This is just a single, unbelievably strong, highly conductive, 1-atom-thick layer of graphite. It is literally revolutionizing electronics today.
Section 3. Chains, rings, and hydrocarbons. The magic of catenation. So we've seen how pure carbon behaves, but organic chemistry really kicks into high gear when carbon starts mixing and matching. Remember those 4 handshakes we talked about earlier? Well, carbon has this totally unique ability called catenation. That basically means it can bond with itself over and over again to form massive structures. It acts like a master architect. For step 1, it can form endless straight lines or long chains. Step 2, it can branch those chains out, kind of like the limbs of a tree. And for step 3, it can even loop back around and hold hands with itself to form closed rings. This infinite structural variety is exactly why there are millions of different carbon compounds. The absolute simplest of these compounds are hydrocarbons, which, as the name suggests, contain only carbon and hydrogen. We basically categorize them based on their bond types. If they only have single bonds, they are alkanes, like methane gas. If they feature double bonds, they are alkenes, like ethene. And if they step it up a notch to triple bonds, they are alkynes, like ethine. But of course, it doesn't stop with just hydrogen. Carbon chains are kind of like a sturdy skeleton, and you can attach different functional groups to them to completely change how they behave. Attach an OH group, and suddenly you've got an alcohol. Attach a COOH group, and you have a carboxylic acid. There are also aldehydes and ketones. Just by swapping out a few atoms on the edge of the carbon structure, you completely change whether a substance is a perfume, a solvent, or a preservative. It's wild.
Section 4. Carbon in everyday life. From fuels to you.
All right, let's pull back from the microscopic world for a minute here. All of these chains, rings, and functional groups are the actual physical materials you interact with every single day. Modern society literally runs on carbon. The fuels in our cars and homes, things like petrol, diesel, and natural gas, those are all energy-rich hydrocarbon chains. The plastics and polymers we rely on, from polythene shopping bags to PVC pipes, are just massive synthetic carbon chains. Even the medicines in your cabinet and the dyes in your clothes are carefully engineered carbon rings and structures.
But most importantly, and I really want you to take this away from today's explainer, carbon forms the basis of all life on Earth. Those complex carbohydrates that give you energy, the proteins that build your muscles, the fats that store calories, they are all massive carbon-based biomolecules. Carbon isn't just around you, it literally is you. It is the absolute foundation of all living organisms.
Section 5. Carbon Chemistry Pop Quiz. Test your knowledge.
Okay, we have covered a lot of ground today. Let's do a really quick recall session just to make sure these beginner concepts stuck. Here is question 1. What is the specific term we use to describe the different physical forms of pure carbon, where it's the exact same element arranged differently, like a hard diamond versus soft graphite? I'll give you a second to think about it. The answer is allotropes. Remember, an allotrope is simply a different structural arrangement of the exact same pure element. Fantastic. Let's try question 2. Think back to that Lego block analogy or the friendly person looking for handshakes. How many valence electrons does a single carbon atom have available in its outer shell to form those really strong covalent bonds? The answer is 4. This special property is called tetravalency, and it is the entire reason carbon is such an incredibly versatile builder, able to connect in so many different directions all at once. All right, one last question. This is a slightly harder chemistry one from our hydrocarbon table earlier. We talked about single, double, and triple bonds. Which specific category of hydrocarbon features triple bonds between its carbon atoms? And the answer is alkynes. If you remembered alkanes for single, alkenes for double, and alkynes for triple, go ahead and give yourself a huge pat on the back. You have officially grasped the foundational basics of organic chemistry. So, the absolutely crucial point here is this. Carbon is everything, from the graphite in your pencil to the DNA in your very cells, all the way to the groundbreaking graphene in tomorrow's electronics. Tetravalency and catenation make it all possible. I'm going to leave you with this final thought. If carbon is the ultimate Lego brick that builds our entire world and our very bodies, what will we discover it can build next? Keep that curiosity alive, keep learning, and I will catch you in the next explainer.